Hello. You can start using your clickers. Two more lectures in the spring break. Test. No? Hello. Can you hear me? Can you hear me good? All right, thanks. So please keep answering. This is some statistics if you haven't seen it yet. It's supposed to be available on a Blackboard. At least I see it on my side. And this is just a reminder. A student asked me, do I scale? Well, normally not. Normally, I try to stick to the absolute scale with certain boundaries, which might be shifted slightly, and I've described why, so you can refer to the lecture. And this is a good distribution and not very much different from others. Recently, well, not very recently, but I've checked your responses to the preview, the pre-course review preview. So, and it might be interesting that 4 answers to the question number 4. The question number 4 was, what is your single most important outcome from taking this course? So the 4 most popular answers are, get prepared to MCAT, 3 students. Bragging about taking physics, 12 students. Get the highest grade possible for this course, 22 students. Make friends, 48 students. So I guess making friends and getting good grade kind of walk hand in hand. I hope that you share, you work together. And about MCAT, I don't remember if I tell you or not, but any MCAT exam is way much harder than any of the exams taken here. So this is what you've learned. This is what you're going to need to learn more to succeed on MCAT exam. Let's see. Well, I guess it's also a good sign. The majority assess your work and your time arrangement correctly. And now there's a next question I want to ask you about is this. And while you are answering this question, so keep reading, I'm just going to switch to the next slide, which has some extra information. I also want to address a couple of things. I always do. Well, number one, anybody who still feel like, actually, almost forgot. You may be at the wrong place at the wrong time. Please refresh the disclaimer from the lecture number 1. It tells everything about this course and about me. Now, I, again, very appreciative for any feedbacks. I have some of them here, And please just look at the screen, choose your answer. First of all, I couldn't read some of them, so clearly I'm not the only one who has a bad handwriting. But what I read, I wish solutions on WebAssign would be available. Well, I'm not sure how exactly WebAssign works. It is set up that after the sixth submission, you should see the solution. But I'm not sure if you, for example, succeeded at the first time, do you have to enter 5 more correct submissions? I don't know. It says 6. Does it mean 6 incorrect, or I don't know. So that's something I'm not sure about. Algebra makes some problems more difficult. Yes, it is. Sometimes it's hard to follow. Well, you see, I've collected most common suggestions. Yeah. And again, I got them every year, every time, roughly with the same percentage. Yeah, the speed, well, speed depends on the amount of material has to be covered over a certain fixed amount of time. And hard to read, I'll talk about it later. Now, go through examples more slowly. More time for new questions. Well, some suggestions contradict each other due to, again, time limits we have, because either I have to cover less example, spending more time on each, or more example, spending less time on each. So I just use my experience, judgment call. Some suggestions related to labs and discussions. Well, some of them actually I forwarded everything to lab and discussion TFs as well, and we have discussed discussions. More problems to practice in discussions. Well, I'll think about it. It's one long problem which composed of several questions, or several different problems which shorter. Nobody knows which approach actually is the best. Nobody knows. So it's more like an art composing discussions in the labs. It feels like me expects us already to know more than we do. Yes, I do. This is a class which, based on certain requirements, again, feel free to say anything because it's anonymous. I don't know who wrote it, but I'd like to address, for example, if you would take in a similar class at, let's say, ITT Technical Institute, or Wentworth Institute of Technology, or Bridgewater State College, where I teach, or used to be teaching. They all have the same name, elementary physics, but the level is different. You're taking physics at Boston University, which is number 50 on a list of 500 best universities. So there are some expectations. That's it. I cannot understand our lab TF at all. This, again, is a very common situation related to a major university which has people from all the world. Some of them just start studying English You know, I've never studied English. So, well, be proactive. If you don't understand a person, just ask a question again. That's it. Just tell, speak slower, or try to ask to repeat the question, you know. Be active. That's it. And problems on the exam not familiar to homework problems. Not familiar to homework problems. Pretty straightforward, nothing surprising. Two different people, two completely opposite opinions. I can never follow the instructor's lectures too quickly. Well, at least you have a video which you can slow down. Now, would be helpful to post slides. I do. On a Blackboard, there's a folder that says notes. You go inside, you see slides. My discussion TF confuses me. Well, it happens. Again, be active, ask a question, try to clarify. And some of the grad students have just this experience of teaching. Some of them have been teaching 3 times already, so depending on the experience, they're all, well, different. It's like winning or losing a lottery, you know. You make one discussion section might get a better experienced TF and another not as experienced. What can you do? You, again, be active. Get from him or from her everything you want to. It was a difficult exam. The exam wasn't challenging enough. What can I say? So I guess I hit the middle, which is kind of a good sign. Some TFs don't make themselves known in office hours. Yeah, well, again, despite the fact that I say it again and again, they might forget. So you entering the office hours, you know it has to be a TF. There is no sign. Ask a question. Who is here for PY 105? That's it. Worksheet, some which I can't understand, in addition to discussions. Well, some faculty issue worksheets for every lecture. I used to do that, now I don't. There is actually a very, very valid study that when a person, a learner, doesn't experience any kind of a certain level of struggle, that person doesn't actually learn. So people confuse nice feeling and successful job very often. So, well, you know, probably now there is a common agreement that we use too much soap. Yeah. So a certain amount of dirt actually could have been helpful for the body, for the health, because that helps to fight. Yeah. Same is true for anything. You know. The brain has to be kind of preheated in order to learn better. There is a study on that. So if the brain just transmits information without trying to rearrange it, it doesn't learn. And another thing, by writing like I do, which nobody can read, I'm actually doing you a favor, because that makes your brain to struggle a little. And again, imagine two students taking the same class, the same lecture. One student have ears plugged in and eyes closed. And another student, well, at least eyes open. Who's going to learn more? It's not a question, of course, the second one, because, well, the brain of the second person processing more information. Do we learn by our heart, kidney, food, eye, brain? So we have to fire up a certain amount of neurons. The more neurons being fired up, the better for the learning. So there are many sensory inputs you can use. When you say a force, that's a certain amount of neurons. But when you say a force and you move, that's a different amount of neurons getting fired up in your brain. When you're just looking at the picture, that's one amount of neurons. When you're making a copy of a picture, that's a different amount of neurons and a different amount of connections. So when you're just sitting, looking, and listening, and feel yourself comfortable, you're not learning. So don't feel yourself comfortable. Try to find something which bothers you and resolve that. Okay, again, expected, well, and about 30% more than expected. And if your grade is not as good as you thought it would be, the general advice is try to recreate your strategy for the last weeks and see what you may do differently now to get better prepared to the next exam. For example, what differs this course from previous is not very active using the Piazza or office hours. I'm asking TFs, very low amount of students using office hours, very low amount of students using Piazza's website as a communication tool. I'm not sure if it's a good or bad thing. I don't know. Nobody knows. However, again, if you have any question, you should be active. And you should be organized. And again, what I mean here is don't wait for too long. Start doing homework as soon as possible. For example, when I checked before the first exam, several hours before the first exam, I still had at least one student who had no more than 10% of the homework grade. That's not very organized. And if you think that learning physics or something else is what the university diploma is about, that's not exactly true. There are other qualities and abilities which, well, people who hire actually value even more than just a grade, than just a GPA. Every year there's a study, a survey of business people and executives, and every year they complain that recent graduates don't have abilities they looking for. Not knowledge, not grades, but certain abilities like being organized, planning ahead. Well, I'm not your parent, so I don't really, it's not my place, but I'm a teacher, so sometimes I just can't resist. Any questions? Moving on. Physics. So that was the last slide we saw. Today is Monday. On Friday. So that's a specific application for the law of conservation of linear momentum when two objects colliding. And you're going to do a similar lab, not this week, next week. And the most important thing to remember is this equation. If we have a system, the total momentum of a system is equal to the sum of each individual momentum of each individual object. But if the net force acting on the whole system is 0, the total momentum of the system doesn't change, stays the same. So if we add those individual momenta before something happened and after, the resultant, the sum, has to be the same. Now, this law involves vectors. So it works for one-dimensional motion, two-dimensional motion, three-dimensional motion. But of course, we're going to start from a one-dimensional situation when everything is happening parallel to the x-axis. And in that case, we have only, well, two options. An arrow, a vector, points to the right, or an arrow, a vector, points to the left. If it points to the right, it must have a positive component relative to this axis. And if it points to the left, we must have a negative component. So let's just do some examples. Well, that's the last slide related to some terminology. We have several kinds of collisions. Most of them are related to either absolutely inelastic collision or elastic collision. The absolutely inelastic collision happens when two objects collide and then travel together as one new object. And elastic collision is a situation when they collide and then they travel again separately from each other. But we neglect any kind of a friction. And if we neglect friction, mechanical energy stays the same. So for absolutely inelastic collision, because they stuck to each other, it has to be some frictional force which keeps them together after the collision. So mechanical energy changes. Here, conservation of mechanical energy is one of the parts of the definition of what we call elastic. Superelastic, it's like a collision with an explosion. The energy after the collision is larger than before. And a regular collision we call inelastic. It means they bounce back, they travel separately, but some friction still had been involved, so the total amount of mechanical energy decreased. These are just definitions. And another thing to discuss is just a pure explosion. So you have a grenade right here on the table, which is dangerous. Don't do that. So one object, then it explodes. What you have two objects traveling away from each other. But if you capture this on a tape recorder and you run it backwards, that's going to be two objects colliding and then forming one whole object. So an explosion is just like this, but back in time. So everything we can write for this, we can write for that. And what can we write? Well, two laws. This is the law of conservation of linear momentum. And in addition to this law, we always can write law of conservation of mechanical energy or master equation, which should include non-conservative forces for this collision, this collision, this collision, and this collision. But for this collision, there are no non-conservative forces, no friction. That describes all the possible theories. So now we're going to solve examples. Let's say you have two cards. Well, we'll be playing with cards on track next week. Good. This is just to visualize what might be happening. So, yeah. Two cards. And you can move in any direction. They can collide, bounce back, travel together. That's it. So just keep in mind this is a realistic situation. And this picture shows one card traveling to the right, another card traveling to the left. One card is heavier, second card is lighter. And we are told that after the collision, they travel together. So first of all, what is the name for that collision? AIC, absolutely inelastic collision. So what do we know about it? Well, now, everything. Don't give away the answer too soon. So, P1, what does 1 mean? Well, different people might assign different meaning to this. So we have two objects. So if there is object number 1, there is an object number 2. And we have two situations, before collision and after. So there is situation number 1 and situation number 2. My personal choice is I count objects number 1, number 2, but I call situations initial and final. So the object number 1 has the initial momentum. The object number 2 has the initial momentum. If we add them up all together, that will give us the initial momentum of the system, the whole system. But in general, the object number 1 might have some different final momentum after the collision. The object number 2 might also have a different momentum after the collision, final number 2. But if we add them up all together, the total momentum of the system after the collision must be equal to the total momentum of the system before. Why? Well, the condition is the impulse transferred to the system has to be equal to 0. And again, to refresh, that means the net external force on the system equals 0. It's because, you see, the impulse of the force equals this, F net external times delta T. So if this is 0, impulse is 0. If impulse is 0, total momentum doesn't change. There is another option. Delta T is practically 0. And again, that's what the word collision means. Something happens very quickly. So the ball hits the wall or the bench and bounces back. This process, touching, takes, well, a fraction of a second. So it happens so quickly, so practically there is no transfer of so, well, in this situation, the collision happens very quickly. So internal forces are not the part of the Newton's second law for the system. Internal forces do not change the total momentum of the system. And external forces, like gravity and normal, cancel each other out. And we, of course, we neglect this kind of friction. So what friction we do not neglect? Between the cards. This kind of a friction. Here. So this friction we cannot neglect. This friction decreases the amount of mechanical energy. Well, now, each momentum is equal to the product, mass times velocity. So m1 v1 initial, m2 v2 initial, m1 v1 final, m2 v2 final. So far, nothing specific. We can write this equation in this form for any collision. Now we must remember, velocity is a vector, momentum is a vector. So how should we take that into the account? Well, normally I do that when I'm writing the next step, numbers. So here, in my mind, each variable v represents the x component of that particular velocity relative to the x-axis, which of course points to the right. And because I always assume so, I don't write those little x anymore. It's in my mind. But if we start plugging numbers, what do we get? 2 kilograms, that's number one, times, well, in general, the component is plus or minus 2. But because it points to the right, it's a plus 2. Plus second mass is equal to 0.4 times. Well, that velocity points to the left, so it should be -1. The x component of the velocity of the second object before the collision is negative. Supposed to be equal to, well, same 2 kilograms times final velocity of the first object plus same 0.4 kilograms times final velocity of the second object. Again, at this point, nothing special is happening. We don't know final velocity. That's actually what we're looking for. But what we do know, because now we realize the fact that after the collision, they travel together. So they must have exactly the same velocity. So final velocity is the same for both, which means we actually can kind of use it as a common factor. Just call it V final. And now we can solve it for the final velocity of this system, or we can say final velocity of each cart after the collision. So 2 times 2 is 4. 4 minus 0.4, 3.6, divided by 2.4. That should give us the final velocity. 3.6 divided by 2.4. That's when you take your calculator and start calculating. So another part of your brain would start acting, would be activated. And the result is, survey says, 1.5 meters per second. Questions? Now, the second question is, what happened to the energy? So, as we know, if friction is involved, mechanical energy changes. We know even more, it decreases because some of that energy goes to heat. So how much? Well, we can calculate the change in the kinetic energy, which actually has to be equal to the work of friction between the carts. What it should be equal to? Well, kinetic final minus kinetic initial, which means that has to be equal to m1 times v1 final squared divided by 2 plus m2 v2 final squared divided by 2 minus m1 v1 initial squared divided by 2 plus m2 v2 initial squared divided by 2. So this is now just a straightforward calculation because we know all the numbers. M1, 2 kilograms. Speed, final is 1.5. 1.5 squared divided by 2 plus M2, 0.4 times 1.5 squared divided by 2 minus. What we're subtracting is the initial kinetic energy. 2 times 2 squared divided by 2 plus 0.4 times 1 squared divided by 2. It has to be a negative number. It will be a negative number, you see. And I think it's going to be something like negative 1.5 joules. I'm going to give you a minute just to calculate, to check. If your number is different, I might need to change my. Sometimes I don't change the slide for a couple of years, and then I realize calculation was wrong. A comma or point was missing somewhere. You know, it might have been done late night. So it's always good to check all calculations you see on slides. So that's 2.4, 1.2 times 1.25, yeah, minus 4.2. Well, this is how far I go. Okay, thank you. Moving on. So all the reasonings we've used now can be applied to many, many different situations. The physical nature of the situation might be different. It could have been an explosion, a person jumping off a boat or off a sled or off a cart, you know. That's what we call a separation, an explosion, which is basically collision backwards. Or two carts colliding, or two ice skaters, you know. So doesn't matter what's happening. They all have the same in common, the same feature in common. One object and then two objects. What was before, what was after doesn't matter. One object and two, an explosion. Two objects and one, a collision. But we always can write the same equations and do exactly the same analysis. Now let's talk about a different example. Absolutely elastic collision. And there are no numbers here because first I want to go through this situation in most general way. Not yet. So you just an object number one, mass number one, initial velocity number one, two initial. This is the picture which we call before. And of course, a similar picture we can call after. Absolutely elastic collision. This name means they move separately from each other. So we had two objects, and still we have two objects. Now, how do they move? We don't know. If we go through a set of specific situations, we'll see that everything can happen. They might not move at all after the collision. They might move in opposite directions. They might keep moving in the same direction. So in general, we do not know. Until the problem is solved, we don't know what will happen. So what do? We start from a situation, they just keep moving to the right. Now, final two. This is what people usually write in every textbook. I don't like that. So starting from that, textbook or a fork, Valentin Voroshilov. This is my situation. M1 V1 to the right, M2 V2 to the right. Why? Because in that situation, I don't have to care about pluses and minuses. This is my situation after. That's before. That's after. M1 U1, M2 U2. I don't use any subscripts besides 1 and 2. 1 means first card, 2 means second card. If I decrease the number of symbols, I decrease the risk of being confused. But what I use a different letter. So V and V means before the collision, U and U means after. And as you know, we could have used any different symbol like star or cloud or square, doesn't matter. And again, I point both to the right. So in that case, M1 V1 plus M2 V2 is equal to M1 U1 plus M2 U2. That's immediately law of conservation of linear momentum. When I start plugging numbers in after, I will take into account which velocity actually has been positive, which velocity actually has been negative. But at this step, at the algebraical step, I don't want to think about it. The next law, conservation of mechanical energy. Absolutely, yeah. Elastic collision means M1 V1 squared divided by 2 is equal to M2 V2 squared divided by 2, plus is equal to M1 U1 squared divided by 2 plus M2 U2 squared divided by 2. Kinetic energy before and kinetic energy after should be the same because there is no friction. Law of conservation of mechanical energy. And strictly speaking, we're done. 2 equations, 2 unknowns. Use U1, U2. But the equation is quadratic. So again, you have a fork. You can solve this equation for, let's say, U1, plug it in here, use quadratic formula, discriminant, 2 solutions. Try both in the first equation, see which makes sense. And I would say that would take an hour. So I want to show you a shortcut. First of all, how can we simplify the second equation? What can we do? The second equation, yes? Cancel 2's, of course. The rule is if you can cancel something, cancel that thing. That's the rule. Now, second step, we actually, it's going to be much easier to solve if we collect everything related to first object on one side and everything related to the second object on another side. So M1 V1 minus M1 U1, m2u2 and u2 minus m2v2. m1v1 squared minus m1u1 squared equals m2u2 squared minus m2v2 squared. Easy enough. Any questions? Now, you see m1 is a common factor. m2 is a common factor. So, next step. m1 v1 minus u1 minus u1 equals m2 u2 minus v2. Second equation, m1 v1 squared minus u1 squared equals m2 u2 squared minus v2 squared. Someone has to say something. Again, we are always looking for something to simplify, make things simpler. There is something we can make simpler using algebra. What is that? It's a trick. Very useful one. So, anyone? If there is a rule in algebra which we can use here, if we find that rule, if we recognize that rule, what do you say? No. Yes? That is correct. That's absolutely correct. That's a difference between two squares. It's very easy to prove. You just multiply, you know, a squared plus a times b minus b times a plus b squared. This cancels, so that's exactly what it is, a squared minus b squared. But here, we can use it. That's going to be v1 minus u1, v1 plus u1, u2 minus v2, u2 plus v2. You see how hard it to read this, how much favor do I give you today? Now again, our brain is a very powerful pattern recognition machine. So if we look at this equation, there is such product, m1 v1 minus u1. And we can see exactly the same product right here. Then m2 u2 minus v2. And we can see exactly same product there. So these two are equal to each other. So if two things are equal to each other, but they on opposite sides of an equality, what can be done? Yes. That's the last step. You can cancel these two, because these are equal to each other due to the first equation. So the first equation stays, but the second equation now is much easier. It doesn't have any squares anymore. Two. Okay, I'm going to go to, I think I had it, so, okay. I'm going to just write it again on a blank slide. So the law of conservation of linear momentum conservation plus the law of conservation of mechanical energy, no friction, together can be replaced. Well, still, they should. m1 V1 minus U1 equals M2 U2 minus V2. V1 plus U1 equals V2 plus U2. Done. This solves all the problems. You just plug in the numbers, and you don't have to solve any quadratic equations anymore. It's a simple system which usually can be solved by adding or subtracting two equations to eliminate unknowns. All right, thank you. We're going to do specific examples of a problem like that on Wednesday. And if you have any question, please send me an email, go to office hours. An announcement. The solution to the exam is on the Blackboard. You should check. And if you have any question, you should see me, and only me, and see what happens. Yes.
Do you have physics today or this week?
What do you mean?
You do a physics lab, I mean?
Yes. This week, labs on the regular schedule.
Also, where is the sign-in sheet? Because I didn't get to me.
Hello, who's having sign-in sheet, please? Yes. Yes.
So why you start with why you choose like the two cards pointing at the same direction for the before situation?
Because that makes my general analysis easier. That's it, just to simplify algebra. When you have to solve a specific problem, if your actual velocity points to the left, that only means you're going to use exactly the same equations, but number for this variable will be negative. That's it.
Yes.
That's it. So I'm solving all possible situations in one. If I pointed all arrows to the right, after that, all I have to do is use a positive number for an arrow pointing to the right and use a negative number for an arrow pointing to the left. That's it.
Okay. Okay.
If again, I'm going to do specific examples on Wednesday using this approach again and again and again, at least 3 more examples.
Okay.
And that should, help to clarify this.
Okay.
I just didn't have time today. Yes.
I still have a question on this problem of the exam. Because in the discussion, I was told by the TA that at the highest point, the vertical vertical
Trajectory.
velocity is 0, and
No, not velocity is 0. Velocity is not 0. Only the vertical component of velocity
yeah, but I
is
also
0.
point out here. My question is the equation for the velocity is the x plus y velocity?
That is the correct equation.
So
But your math is wrong because, well, you see it's 0.
yeah, because the vertical is 0 then.
Well, if you do this correctly, you made a mathematical mistake.
Oh yeah, should be just this. Yeah,
Exactly.
Yeah.
But there is a rule that if you did the work correctly, but you made mathematical mistakes, you shouldn't be losing the whole. Only Yes, you should have a partial grade for this. So this is a grading mistake. But I need. See, first of all, I need to move out as soon as possible. Thank you. Yeah, everything can go.